afternoon, everyone. Welcome to the very last session of the summer school, and Dr. Dufourq will share with us his last parts of his mini course. Yeah, and I'm really glad to see that there are still many people joining us. So Emmanuel, that means that you really hit the nerve of many people. They just want to know how the story ends, although the story never ends, but is how the introductory story ends. Yeah. So Emmanuel, before I ask you to start, I just want to remind everyone, although we reminded everyone already through all channels, that after this session, probably around 3:30 or depending when Emmanuel ends, we will have a small closing ceremony, yeah? And there we will reveal the names of the winners of the book prizes, yeah? So please, don't leave the meeting after the lecture, because we are using exactly the same Zoom link, so there is no need to go in and out. We might just wait a minute or two in case other people join as well, because we invited also all the other lecturers, so they might join around 3:30. So Emmanuel, I did my my advert. You're most welcome to start. Thank you very much.
Great, thank you. Thanks everyone for joining, especially on a Friday afternoon. And I'm really glad that all of you are here, because today is going to be an exciting mini lecture. And okay, I put my timer on for 3 parts. Today will be broken in 3 parts. The first part will be wrapping up the gentle introduction to convolutional neural networks. Then we will spend a little bit of time on 2 notebooks. The first notebook will show you how to manipulate some audio in Python. We'll download a nice vocalization of a double-collared songbird from Xenocanter, which is a public open source public repository for bird vocalizations, and we'll show you how to generate the spectrograms. And then in the last part of today, I will show you how to at least go through a pipeline on how to build a convolutional neural network to classify vocalizations of the world's rarest primates. So today will be quite fun, and hopefully you will enjoy it with me. Let me share screen 1. Right. Okay, great. Okay, so this is roughly where we left off yesterday, where the idea is when we build any machine learning algorithm, but more specifically convolutional neural networks, we want to start with the simplest model possible. And the simplest model would be to take in the input and have one convolutional layer followed by the softmax output. So this would be the absolute basic thing. And it's always a good idea just to start off with a very simple model, just to make sure that your full code pipeline from the beginning to the end works. And then gradually we can add complexity. So here, for example, we're taking in our inputs. We have one convolutional layer followed by a max pooling layer, followed by another convolutional layer, and then the softmax. So we can gradually add more and more complexity. And likewise, we can have our convolution, max pooling convolution, followed by multiple fully connected layers before the softmax output. So it's always a good idea to gradually add complexity. Don't start with a very complicated model, because you might run into bugs in your software and waste a lot of time trying to fix bugs. Rather start with a simple model first. So just to give you a full idea of what the model might look like, let's say we have 2 convolutions, one fully connected layer and an output layer. The general recommendation is that the convolutional layers will use the ReLU activation function, and the fully connected layer will also use the ReLU activation function. And we've spoken about this quite a bit now. that the output layer will have the softmax activation. And we also spoke about how does the network know if it's doing a good job. And this was the loss function that we spoke about. We spoke about categorical cross entropy. So this would be what you would probably use for a classification problem. One thing that we didn't really speak about is the optimization algorithm, which is used to update the weights. Now, this is a field of research on its own, and there are many optimization algorithms that exist. There are more modern ones, such as Adam, and there are older ones such as a stochastic gradient descent. All of these optimization algorithms that we use in neural networks are variations of gradient descent. They're just more advanced, and researchers make them more advanced to be less prone to getting stuck in certain areas of this complex search space. So this is generally the way you would start, is you would have a simple network with the ReLU layers and the softmax layers, and you would have a categorical cross entropy loss function. This is the way you would start if you wanted to build your architecture from scratch. In other words, you wanted to design the architecture yourself. What if you didn't want to design it yourself? What if you are someone that enjoys academic literature and wants to turn to the literature? So what you could do then is you could make use of CNNs found in the literature. So AlexNet is not a modern CNN. It's been around since 2011, 2012. And it's made up of pretty much everything you already know. It's made up of convolutional layers and max pooling layers. Here you can see that the X and the Y are becoming smaller and smaller with the max poolings. Here are more convolution layers. And then we have our fully connected layers here represented as just a rectangle, but you can think of this as 496 units, the circles. And here's another fully connected layer also with 4,096 units. And finally, in this case, a 1,000 softmax output, because this was applied to a data set that had 1,000 classes. So you can design one from scratch, from yourself, or you can look at what other people are doing in academic literature. Here's another example of another convolutional neural network from Oxford University called the VGG16, and it is also made up of everything you know, convolutional layers with the ReLU activation function, with max pooling, and then we have the fully connected layers. The diagram is represented differently here, with the rectangles going this way. And our 1,000 class softmax output here. Now, of course, what you can do as well is in your particular area of application, you might look at what other people are doing. So for example, I would look at bioacoustic research articles that use deep learning, and I would look at what kind of architectures the researchers are using, and I might decide I want to adapt one, or maybe I want to draw inspiration from their architecture to have design my own. So why are we interested about learning about existing architectures? Well, researchers in deep learning put a lot of effort to try and create new architectures that achieve state-of-the-art performance in various application domains. For example, in computer vision, in text processing, in speech recognition. The respective researchers put in a lot of effort. So studying what is being done is a good idea. And also when you jump into this field, you will realize that there are many decisions that the user has to make. How many layers, what activation function, how many epochs, what's the batch size, how many filters, what's the size of each filter. So there's many hyperparameters. So taking time to study existing architectures is always a good idea. So now that we've learned about CNNs, you know, the first question that you should ask is, can I train such CNNs on my computer, on my desktop, on my laptop? And it will depend on the size of the data. If the data is made up of very complex, large images, you might not be able to load a large batch size in your network. Joseph, you have a question?
Yeah, well, Nomzan. Do you mind just going back 2 slides back? I had a question about that. Yeah, that one right there, the Oxford one. So just to clarify, those fully connected, is that the actual hidden layer section? Is that like the actual neural network? Right, and then the thing to the right that looks like red or something, that's just the output, which we use, whether sigmoid or whatever it is, just to, depending on our question. And then the stuff before that, that's the convolution. Each of those stages is what we can call a convolution, right? Sorry, can you hear me?
Yeah, I can hear you.
No, I'm just trying to get confirmation. So each of these stages is called a convolution, or is that whole thing called a convolution?
Okay, so the full network from the start to the right is called a convolutional neural network. The part on the left that is made up of the convolutional layers and the max pooling layers is typically referred to as a feature extractor, because it's extracting features. And the part on the right is what would be called the classifier, because that is what is the fully connected layer is responsible for the classification. So the left part before this, and including this red block, is convolutional and max pooling layers, and the right, the blue and this yellow is the fully connected layers.
Oh, all right. Okay. And I don't know if it's part of this, but do we go into how do you decide which nodes, how many nodes are appropriate for which hidden layers? What are we going to do that today, or is that something that's already been done?
No, so we're not going to do that today. That is a complex discussion. So optimizing deep neural networks is a very exciting research area. There are many different ways of trying to do it. The simplest would be to just do a random search across hyperparameters. You could do a grid search across hyperparameters, which is very time consuming. Or you could turn to another type of machine learning algorithm to find these hyperparameters. In the past, we've published a paper that uses evolutionary algorithms to optimize these neural network architectures. So you can think of it as an AI for AI. That is the one way of dealing with it as well. So it's not a trivial task. It's an active area of research, but the simplest way to tackle it would be to do a random search, for example. Great. Momzaza?
Yes, thank you very much, Mr. Emmanuel. I actually want to ask about the general architecture of CNNs in special regard to their robustness. I know that there have been cases where literature has shown that a single pixel attack can confuse a CNN from classifying something from its true class to a false class. So my question is, what has been done? Like, what is the current like research or probably engineering techniques that are being used to ensure that CNNs are more robust?
Yeah, so what you're referring to is adversarial attacks, which is an area of research on its own. I think I can honestly say that I'm not following this area. So I don't know what the state of the art on adversarial attacks is, but that would be what you would look for if you wanted to explore adversarial attacks and try and find a recent survey paper. I'm not sure. And I can honestly say that I'm not worried, because there wouldn't be a lot of cases for which there would be an adversarial attack on trying to do ecological tasks. There are many use cases where you would deliberately try to confuse a neural CNN, but in applications of machine learning related to wildlife and ecology, I can't imagine many reasons why, you know, someone would deliberately want to prevent the network from helping with the, you know, biodiversity assessments, for example. So that's why I'm not particularly following what's going on in this space. Okay, sorry, that's not a great answer, but it's an honest answer.
Okay, thanks.
Okay, no more hands up for now. So in terms of training them, you can train them on, you can train these neural networks on your CPU, the central processing unit, but most modern desktops and laptops have maybe 2 or 4, in some special cases, 8 CPUs. So there's only a limited amount of things you can do in parallel. And CPUs are very fast, specialized hardware, but you are limited to the amount of tasks you can do simultaneously. On the other hand, GPUs are made up of many of these like CPUs, if you want to think of it that way, but they are less sophisticated in terms of their, let's say, the computational power per CPU. So a CPU has quite a high performance, but the cores within a GPU are less high performing, but there's many of them. There's up to 4,000, 8,000. So you can do many tasks in parallel. And these GPUs are what people use to render animations, for video games, for image processing, because you can process many pixels simultaneously. So it turns out that this is a great technology for processing CNNs, because the CNNs, essentially what is happening, it's just many matrix multiplications and matrix additions and applications of activation functions on these matrices. So given the hardware, you can do many tasks in parallel, and that's why GPUs are actually a great technology for deep learning. Allows us to do a lot of these matrix multiplications and additions in parallel. Since these specialized hardwares have many cores, and each one can be responsible for a particular small task. So if you don't have one of these, what is the result? The result is just that your training will take very, very long. Or your batch size would have to be very small as to the amount of data that you're processing. And it just makes the computation a very lengthy one. So what if you want to do some of this research and you don't have a GPU? You can turn to the cloud. Google Cloud Engine, Amazon AWS, Floyd Hub, and Microsoft Azure. There's probably a whole wide range of them these days. Are cloud services you can use to train some of these CNNs. So, you know, one strategy you might take is to develop some of this code locally on a local computer. And then when your full pipeline runs is you just log on to an online service and you train your model. Maybe you train it over 1 or 2 hours and you end up paying $1 or $2. That's if you just wanted to do a once-off training. Some of these things, services charge from $1 to $4 to $10 per hour, depending on how many of these GPUs you are actually requesting. And there are other tools such as Google Colab that also have some GPUs in them that allow you to run some of your code. So I guess the trend with time is service providers are making it easier for us to train these neural networks compared to a few years ago where it was quite expensive to start building these models. So the last thing I want to end on for these lecture slides before we move on to some of the practical stuff is to do with image augmentation. So something I haven't mentioned is that these deep neural networks and convolutional neural networks require a lot of data to train a robust model. What if you don't have a lot of data? How can you then still tackle the problem? So one technique in computer vision is to apply some kind of augmentation. And here is an example of some of the things you can do. So you can have your original image and you can rotate the image, you can move the image around, you can crop part of the image, you can blur it, you can add vertical and horizontal lines, you can add a noise. There's lots of things that you can do. There's actually many of these techniques to generate synthetic data. So if you have one image, from this one image, you can create maybe 20 new images just by applying all these kind of techniques, which means you can easily scale a small data quite significantly, which is great, because then you have a lot of data to train these convolutional neural networks. So I guess then, one has to ask themselves, can you just blindly use image augmentation, or do you need to think about it? And you need to think about it. There are certain application domains where certain of these techniques won't make sense. So can any of you think of when, for example, flipping an image might be a bad idea? So a horizontal or a vertical flip, in what use case might that be a bad idea? In the case of building a classification model to detect pictures of cats, flipping would not be a problem because you could have an upside down cat, or if it's left to right or right to left, it doesn't matter. So could any of you unmute and just discuss a particular use case when you think it wouldn't work? Hello. Isaac, I think you've muted yourself.
Yeah, okay. With reference to the flipping, if we should do a vertical flipping, we might have end up getting like the image upside down, of which in the normal sense we don't take a picture with the cat upside down. So I believe doing a vertical flipping might have generated an image which it will be a noise in the data set. That's what I can say about that.
Okay, but can you suggest an application, like a particular application where you think it wouldn't work?
Yes. Okay. Maybe if you want to do a classification of maybe a dog or cat, and then it happens that maybe the data that we have is not enough, and we want to generate a couple of data to augment or to add up to the existing data. I think that's an area of which maybe doing a vertical flipping we are likely to have an issues with the data that we have generated.
I suppose, but I mean, there are many times where a dog will lie on its back and the head might be looking backwards. So I think a vertical flip would be okay for pictures of cats and dogs, because, you know, cats and dogs are often doing all sorts of acrobatics and they could be upside down. So I think it would still work and would still be useful. So maybe another kind of application domain might be more problematic. So there have been some suggestions in the chat. Anyone want to describe a use case where it would not work, where one of these would not work? Matt?
I might have a simple example. If you want for some reason to predict right hands, if you flip the images to left hands, and that's not going to work.
Yeah.
It might not have a relevant application there.
Yeah. Yeah, that would work. Let's go in the chat. Vertical flip of a house. Yeah, sure. That would probably be abnormal. Identification of fish. I think if you flipped it, it would still be useful, because if the fish is swimming, yeah, I guess a particular type of flip would not be appropriate. Horizontal would work. Vertical probably wouldn't work. I think the simplest use case to describe would be numbers, right? Flipping a 3 does not look like a 3 anymore. It looks like an E, like a capital E. So yeah, so there are many cases where one has to be careful. Now, with reference to acoustics, one can think of many such augmentation techniques that would not work. For example, if your species is vocalizing within a particular frequency range, there are techniques that allow you to manipulate order to increase or decrease the pitch. So increasing the frequency or decreasing the frequency. This would result in unrealistic data. In speech, you can also accelerate or make the audio slower. Now, this would result in spectrograms that are not realistic as well. So with regards to acoustics, we also have to think carefully about what type of augmentation, and flipping would definitely be a very bad idea in acoustics, because it would result in spectrograms that are not at all representative of the true calls of the animals. And you can just think of the gibbon calls, where a horizontal or a vertical flip would be completely inappropriate to generate representative data. Okay, so this is it for our slides on the introduction to CNNs. Okay, it's exactly past, so this is pretty much where I wanted to be, but maybe there are some questions in the meantime. We can take a few questions and then move on to one of the two pracs. So are there any questions?
Doc, yeah, I think all the methods that we have seen, they also have the very areas of which they are applicable. For instance, if we should consider cropping to also have an area where doing cropping we might have generated some images which it will not be relevant. So I think all the methods also have their all the techniques also have areas of which they can be applicable and some areas that they cannot also be applicable. So it's not only flipping. That's what I'm thinking.
Yeah, you're right. Yep, you're absolutely right. Are there anyone else has a question about any of the material with respect to CNNs?
Hello.
Hello.
Sorry, I had a quick question. You remember we were speaking about, I think you said a bonobo. I forgot the name of the species of animal you're speaking about in question, and that you were looking for, and you were sort of using the sound of it, obviously the acoustics. When you're doing your training now at the end to say, okay, to sound like that final animal sound, let's just say a goat, like the sound that a goat makes, would you train that, the sample that you use to say this is what a goat is supposed to sound like, would you train that with the actual background that you do? Or would you I don't know if you're getting my question.
Okay, so I didn't hear your full question, but I think I understand. I think there's just one mic we need to mute. I think it's.
I've done it.
Okay, great. Okay, so I think okay. So I think your question was, do you need to train it with the background sound that you will apply it to? I think that was more or less what you were alluding to. And I think that the answer to your question. Okay, so what's the or part?
In like a lab.
Okay. Okay, I heard the keyword, the lab. Okay, so the question is, could you get the vocalizations in the laboratory setting, or do you need to train it within the environment that you will apply it to? That's a great question, and I think you will be able to answer your own question at the end of the first prac. So, if at the end of the first prac you're unsure, then bring up the question again. Okay, any other questions? Okay, so far no questions. Okay. So for the next 30 minutes, so I'll put a new timer on. For the next 30 minutes, I want to spend some time on this prac, which is not a very complicated, well, let me say, relatively not difficult, because everything is relative. And I just want to show you how to do a little bit of audio manipulation. Can you see the code clearly, or do I need to zoom in a little bit?
I think it's fine, Emmanuel.
Okay. Okay. So if it's okay, maybe everyone just give a thumbs up if you can see the text, if it's big enough. Okay. Okay. So I'm just executing this on Google Colab. You all know of Google Colab, right? Is there anyone who's not been exposed to Google Colab? Okay, so there's no hands up. Okay. So what I would like, okay, zoom in a little bit. I can do that. Okay, is that okay? Okay, so Jiva, are you okay now? Okay, great. So I want to download a file that we will manipulate, and this website is It's called Xenocanto, and it is a public repository where people upload vocalization recordings of birds. So if you go to the home page, every day they showcase a different bird and the vocalization, and there's a little bit of information, and you can also explore. You can explore within the countries, and you can get different vocalizations. You can also search by particular taxa of species. So based on the taxa, you might be able to get different recordings, and then you can zoom in. You can see whether the recording has taken place, and at the bottom you can access the recordings. Each recording has the name of the recordist, the location it was taken in, the length of the recording, and the quality. So the quality ranges from A to E. A is the best. That means the recording is primarily just focuses, you can mainly just hear the species, and E would be, there's like a lot of background noise. So actually, let us go to one made in Cape Town. So here, so this, I really enjoy this website, and this is, this relates to I think the second to last slide of my talk on last Monday is how everyone can help. And everyone can help because you'll see that in Century City, you can commonly find this gray heron, but nobody over the years has uploaded a recording, and I was the first person to do that. So you can, so if you click on it, you access the data for the recording. So there's me, it's the date I recorded it, the time, the location, and you can add some notes. So if you're a birder and you know a lot of specifics, you can start to add a lot of these details. And of course, you can play and listen and listen to the sound. So what we want to do is download the file. So you can just click on download audio data, and I've downloaded the data. Now, I think Xenocanto has an API that allows you to download in bulk and do all of these things. And so what I've done is I've downloaded the file, and I've just renamed it. I've renamed it to this short name, because otherwise the name contains a whole bunch of other things. So now we have our file, and I've uploaded it. I've uploaded it here to the Google Drive. Actually, let me show you something else. Let me show you Sonic Visualizer. Let me show you what that looks like, because I mentioned Sonic Visualizer in the presentation. So this is Sonic Visualizer, and I can drag and drop my recording in here. This is the amplitude value, so this doesn't tell us a lot of information, but I can generate the spectrogram, and you can zoom in, and you can zoom in on the frequency as well. So this is what the spectrogram for the gray heron looks like. You'll notice if I zoom out, there's this difference in color here. And that is just a result of applying a low pass filter. It just cuts out all the high frequencies, but that's just a separate detail. It doesn't matter. I just wanted to show you what Sonic Visualizer looks like when you import an audio file into here. So this prac what we're going to try and do is we're going to try to extract some of these calls. So this is the gray heron. This is not the species that I put in the notebook. This is the one, so let me download it again, and let me just rename it. Okay. So let me show you what it looks like. Something is going on here. Let me fix this quickly. Right, okay. So this is the vocalization of the double-collared Sunbird. It's actually a really nice song. You hear it in Cape Town quite a bit, I think in winter. It's a very distinct sound, you can't miss it. It's a very joyful sounding bird. So we want to write a little Python script that will extract some of these spectrograms. So that's our goal. So now we've got the file, and I've put it here in my Google Drive. And the library that we can use to process audio, there's many of them, but a good one is called Librosa. So of course, I always recommend that if you use a new tool, to spend some time and study the documentation. So I would always recommend coming to the documentation for the library and reading a little bit about it before using it. But I've used it a lot, so I'm not going to start digging into this now. And we can just import it. So it already exists in the Google Colab Python environment. So how do we read in an audio file using Librosa? Here is the Python function. So we just say librosa.load, and we specify the file name, and we can also specify the sampling rate at which the recording was made. Now, how do I know it was 44,000 hertz? I can go to the recording and see that the sampling rate for the microphone was 44,100 hertz. So I can just specify here that the sampling rate is 44,100 hertz and say librosa.load. Now this function will return two things, essentially. It returns the amplitude values, which is just a long vector of numbers. And it also returns the sampling rate. So now if I print the sampling rate, I can confirm that indeed it is 44,100. So now what if we take a look at this audio variable? So let me just add a cell. So it's just an array of numbers. It's just an array of numbers, and I think it's a NumPy array. Yeah, so it's a NumPy array, and this is the length. So it's a really long vector of numbers, the amplitude values. So how would I determine the duration of the file? So we know that the definition of sampling rate is the number of data points per unit second of time. And we have this many data points in total. So if we take this many data points divided by the sampling rate, then we can get the duration of the file. So this is what I've done here. I got the length, which is measured in the data points. And this is the rate of how many data points per second. So then I can find out what the duration of the file is. So it's 43 seconds, 43.7 seconds. and I can confirm that on the recording. So here we see the length of the file is 43.7 seconds, and the sampling rate. Is everyone okay so far? Just put a hands up or thumbs up if you're okay on the code to read in an audio file and the logic about getting the length of the file. Okay, so there's 2 thumbs up, 3 thumbs up, and everyone else, are there questions? Okay, no questions, but feel free to interrupt. So I would say this is the most important part, because reading in the audio file is what allows us to carry on and to do any form of manipulation. So we're just reading in, we're getting all the amplitude values and with how many amplitude values were recorded per second. Now, there is a library that allows us to play the audio. So I'm not sure if I play a sound, will you hear it? I don't know if that setting is...
Yeah, it depends from the settings. I'm not sure. Let's try.
Okay, let's try. So let me go here, and you can let me know if you can hear this. Why can't I play?
So far, we can't hear.
Okay.
We don't hear it. Yeah.
Okay, let me see. Is there anything I can quickly do? Share computer sounds. Okay, needs my password. Clearly don't even know my own password.
Your machine password, huh?
Yeah.
Okay.
Let's try now.
Negative.
Wait, something is flashing on my screen. Wait, let me try and see if there's something that's preventing me right now. Okay, I've got share computer sound on. Let me see if I play this one.
Yeah, that we can hear.
Were you able to hear that one?
Yeah, yeah. Thank you.
Okay, so actually maybe I cannot do that. Let me try one last time. Were you able to hear that one?
Yeah, yeah. Thank you. That was great.
Oh, now it seems like I can't hear anyone else. Let me remove this. Okay.
Can you hear me?
Looks like I might have lost my sound now.
Okay, we can hear you.
Okay, okay. Were you able to hear the vocalization?
Yes, yes. In
Okay.
both cases. Yeah.
Okay, great. Okay, so great. So then basically this demonstration worked. You can use this audio library to play back sound. So now essentially we can recreate what we saw on Sonic Visualizer by just using matplotlib and just plotting these amplitude values. So we can just plot the values and we can see the amplitude values. Now this is not useful for us because we can't see the change in frequency. So building a convolutional neural network on this wouldn't help us to classify sounds. So now what we can, so this one plotted all of the amplitude values, but what if we only wanted to plot for the first second? So now if we want that, we can then focus on the first second. So from amplitude value 0 all the way up to 44,000, because the data points are not represented in unit time. They are represented as amplitude values. And for 1 unit time, we have 44,000 data points. So if we want to plot the amplitude values for seconds 0 to 1, we have to plot from 0 to the sampling rate times 1. And this is essentially the amplitude values. So it's a little bit of silence, and then the audio file starts. So similarly, if we wanted to plot for seconds 1 to 2, how would I have to write this piece of code? So this one was for plotting seconds 0 to 1. If I wanted to plot for seconds 1 to 2, how would I modify this? You can type it on the chat. Yeah. So all of these suggestions are indeed correct. We would have the sampling rate times 1, and then we would get the points up to the sampling rate times 2. So I think you are all comfortable with how we extract and work in this amplitude to second domains, where the data points are not in seconds, they're in the amplitude value. So we have to use the sampling rate when we want to extract certain parts of the file. Is everyone okay with this idea? Can you give me a thumbs up that we're not working in the time domain, where basically we have to use the sampling rate to get particular sections in time? Constance, you've unmuted. Do you have a question? So 2 of you have unmuted. Do you have questions about this? Okay, I suspect those were accidents. Is everyone else okay? Can you give me a thumbs up? I'm seeing less thumbs up. So I don't know if I'm losing you or if it's just Friday afternoon. Okay, so there are some thumbs up. Okay, great. Thanks. So now a neater way of doing this would be, instead of writing the actual values of the sampling rates, is you can just use the variable, because we've already got this value stored as a variable when we read in the audio file. So remember, when we read in the audio file, it gives us 2 things. It gives us the amplitude values and the sampling rate, so we can reuse that. To make it neater, And here is the NITheP one. Lilia, can you just unmute, please? Mute, please.
You have a go, Julian.
So, it sounds like there's cartoons playing in the background.
I just muted. Yeah.
That's fine. So this is a neater way of doing it, where now we just use the sampling rate and we put in the value. So it's just neater. So now, of course, we can use this to play back the specific audios. So now we can say we can use this library, and we can say I only want to play from seconds 1 to 6, and then you can play back the sounds. Now seconds 1 to 6, if we look at our spectrogram for this audio recording, so if you look at the top here, at the top where my mouse is, this is in time. So this is 1 and 6 is here. So 1 to 6 would be this this call bout. Sometimes we call multiple phrases of vocalizations as a calling bout. So 1 to 6 would extract this calling segment of audio. Now is the fun part. Now is where we create the spectrograms. So LibRosa has built-in functions that allow us to create the spectrograms. And if we want to do that, we say librosa.feature.mel spectrogram, and we provide the amplitude values and the sampling rate. Now, I haven't formally defined the Mel spectrogram. Essentially, it is a spectrogram in the Mel scale, and the Mel scale, without giving a most formal definition, is a scale that is relative to the perceived change in frequencies that our ears can hear. So our ears, if there's a small change between 500 to 600 hertz, we can perceive this quite easily. But between, let's say, 10,000 to 15,000, our ears can't perceive this change as easily. So we can convert into a Mel spectrogram, which is more suitable for our ears. And if we do so, if we use this function and we store it in a variable s, we have our spectrogram. And the Mel spectrogram, the default values for the y-axis is 128, and the y-axis will depend on the number of data points in the audio file. So, and we can visualize it. So here is the visualizing of the spectrogram for the entire audio file. And it's somewhat similar, or at least should be very much similar to this if I zoom out. It is roughly the same idea, is we can visualize the spectrogram for the entire file. So this is the code that allows us to generate the spectrogram, and this is the code that allows us to visualize the spectrogram. Essentially what this does is it just converts the values into a different scale for us. So I think you would agree that it's actually, from a programming perspective, extracting extracting a segment of audio that contains a vocalization event and generating the corresponding spectrogram from a programming perspective is quite easy. It's essentially one line of code to generate the spectrogram, and it's just using NumPy to specify which seconds you want to target a particular segment of audio. So if we wanted to generate a spectrogram for seconds 1 to 6, it's the same line of code to generate the spectrogram, except that now we say we want the sampling rate from 1 to the sampling rate to 6. So we focus on that segment of audio, and then we can display the spectrogram. And that is essentially the same as zooming in on Sonic Visualizer and looking at seconds 1 to 6. So do you agree that actually extracting spectrograms is not too bad? It's one line of Python code, and you just need to specify what's the start time and what's the end time. And you do that by converting from seconds to sampling rates. So in our case, 1 times sampling rate and 6 times sampling rate. Is everyone okay with this? Just give me a thumbs up if you're okay. That essentially, it's actually quite manageable to extract a spectrogram. So this is quite nice. Now we can extract spectrograms, which means we're quite far in building a data set. So the only thing you still need is to annotate your file to say from seconds 1 to 6, there's a vocalization event. From here to here, there's no vocalization. So these things that you're seeing here is probably another bird in the background. The strong signal is the double-collared, the southern double-collared songbird, and this is probably another bird that you can just faintly hear it. So these the brighter ones are the main ones we're interested in. All this other stuff is another bird in the background. So do you agree that in theory, we could build a CSV file and label the start and the stop time for each of these main vocalization events? Do you agree that we could, in theory, do that? We could go through these files and say, okay, from 1 to 6 is a vocalization. Then from 8 to 12, there's no vocalization. From 14 to 18, there's a vocalization, and so on and so forth. Do you agree with this? Let me know in the chat, yes or no, you don't agree. Okay, so one person agrees that we could, in theory, create a CSV file. Namzaza says we can, but it's a costly thing to do. Yep. Okay, so in theory, it is something we could do. Right? Okay. Now, we can, so staying on this topic, we can visualize and generate these spectrograms that do not contain the southern double-collared sunbird. So, for example, seconds 32 to 34 do not contain the sunbird. So let us check. 32, so 32 starts here, 32 starts here, and 34 ends here. So there's no Sunbird in this area. And this has extracted a spectrogram that does not contain the Sunbird. Here is the Sunbird. This one is, it's another, some background, maybe one or two, maybe three or, yeah, one or two other birds that are vocalizing. Here, it's the same idea, seconds 37 to 39. This one contains a vocalization. So 37 starts here, and 39 is here. So here clearly in this within this time stamp, these two timestamps, there's clearly a vocalization event, and here's the spectrogram. So now, what I want to show you next is the question that was raised earlier. Do we need to, what happens if we record in a laboratory setting and we want to, do we need to record in a laboratory setting, or do we need to record within the environment that the bird is? And what happens if you record in a laboratory setting? Could you get away with it? So how about if we combine segments of audio together? So this is segment one, data segment one. Data segment one is obtained here. It does not contain a vocalization event. So here's the spectrogram. So data segment one is 2 seconds of audio that does not contain a vocalization event. And data segment two is also 2 seconds of audio that in this case does contain the vocalization event. So what if we can combine them somehow? What if we say we attach a weight to data segment one and a small weight to data segment two, and we visualize the spectrogram? So now what we have is 2 seconds of audio that contains both the background and a vocalization simultaneously. And we can play around with these weights. So let me reduce this to 1 and visualize the spectrogram. Now here, you can see more of the vocalizations of the Sunbird. And that is because segment 2 is the one that contains the Sunbird. So if I increase the weight here, it should be even more visible. And if I decrease it, then it's slightly less visible. And if I increase the background noise even more, now the Sunbird vocalization is even less visible. It's mainly the background noise. So we can blend in 2 audio files of the same length, and now we can create synthetic data. We can have our vocalizations maybe recorded in a laboratory setting, and we can inject or superimpose all sorts of background noise. So if we have a recording that just has rain or a river stream or other animals vocalizing, we can take our main vocalization event and we can combine it with all of these different background conditions and create a massive synthetic data set. And this is essentially what we do in practice. Because maybe we don't have enough data for the particular species, we can create synthetic data by injecting all of these different background noise conditions. And this is a great way to reduce the number of false positives that your model might make. So is everyone happy with this idea that essentially we can combine the amplitude values for two audio segments or more, right? So we could add more here. There's nothing that restricts us to only using 2. We just need to manipulate the weights somehow. And this is a great way to generate synthetic data. So if you have a recording for which the background noise is not very strong, you can create all the synthetic data. Joseph?
Yeah, well, so data, or are we speaking about the data used to train the model to see, well, this is what the hawk or whatever bird, sorry, I forgot what the bird's called, or what the bird sounds like, because that was what my initial question was about. So in this instance here, you're saying generating a synthetic data set, a larger one, right? So that you have more to train your model against. But my question was about the actual data that you use to say, this is what it's supposed to sound like. Is that the thing that you would use just a pure lab audio sample for, or would you use an audio sample that's confirmed of the goat in the savannah? I don't know. Well, I don't know if there's goats in the savannah, but you get what I mean.
Yeah, so it's less about the environment, like in the savannah, for example, because you can create synthetic background noise. But in practice, you wouldn't really be able to get laboratory vocalizations unless if the species is in captivity, which would probably be a bad idea in the first place. So in practice, for example, with the gibbons, there was no gibbon in a lab. So we took the acoustic data as is with all the background noise as is in the rainforest. So I think that answers your question. Maybe you can let me know.
So you mean that as long as they saw the gibbon and they knew for a fact, no, it's the gibbon that's making that noise, that was enough confirmation
right,
to say that it's a clinical sample, audio sample of the gibbon.
Right. Okay. So if you don't know what the vocalization of the species you're interested in sounds like, then you can't just take a recording for which you didn't have a visual confirmation. With the gibbons, we know what a gibbon sounds like from existing literature. So in that case, it wasn't a problem because that was the only gibbon in that particular area. But if you're unsure of what the species sounds like, or if you're studying a new species and you're unsure, then you would need visual confirmation. In certain cases, two species might vocalize similarly, and the only way to be sure is via visual confirmation. So that would boil down to, do you already know what the spectrogram and what the sound sounds like, or do you not know? And if you don't know, then you might need a visual confirmation. Once you have a visual confirmation, you might be able to then distinguish from the spectrogram and be able to discern from another species. Does that help?
Gyalong, thank you very much.
Great. Okay, are there any other questions about this part? So what I wanted to show you here is, so I'll quickly go through this because it's quarter past, is I have a little CSV file for which I wrote down the start time in seconds, and I made a small label that the vocalization is present or the vocalization is absent. So at second 2, it's present, at 16 it's present, at 20 it's absent. So now what you could easily imagine is you could iterate through the CSV file using pandas, and you can extract these numbers, and you can extract the label using pandas. So now what you could do is you could create two arrays, one to contain the presence audio and one for the absence audio. And then you can iterate through your pandas data frame, extract the start time, and then say, okay, well, I'm only going to extract 2 seconds. So I take the start time in seconds, I multiply by the sampling rate, and then the end amplitude value would be the start index plus the sampling rate times the duration. So if my first one is a start time of 2, I'm going to say 2 times the sampling rate, and the end index would be 2 plus, sorry, this value plus the duration times the sampling rate. And that will allow us to extract 2 seconds from each of these start times. And then I can say, if the label is present, then I append it to my array, and otherwise I just append it to the absent array. And then in the end, I have a small little data set that contains presence and absence vocalization events. So I rushed a little bit through this, but it was basically just combining what we discussed earlier, that I can just run a for loop, and I can just create a CSV file that contains the start times. Now, of course, this was an oversimplification of the idea, but I just wanted to show you that with minimal effort, you can build a little CSV file, and then you can extract the corresponding segments of audio. And of course, we can visualize them. These ones do not contain, and these ones contain. So I'll make this script available. Okay. So now, for the last 10 minutes, I just wanted to show you something, and I guess I thought this was a nice way to end on something exciting. This little notebook is actually, you are the first people to see some of this. This is a new paper. We haven't published it yet. So it's some new data that we've annotated for the gibbons. And so essentially what's going on here is it's just connecting to my Google Drive, and it's just downloading the code, and it's downloading all the acoustic files. But what I wanted to show you is, so here are all the hyperparameters associated with building these classifiers. And here I have a little script that will read all of the audio files and will do some pre-processing. So if you're interested in the pre-processing, you can have a look at the Gibbon paper, which explains the pre-processing involved. This isn't really what I want to focus on in the last 10 minutes. What I want to now go is from here. So now we have our data set, which was pretty much created the same way we've talked about. There's like a CSV file, and it contains the start and the stop time. So now I have, on this little data set, 1,500 audio events and its spectrograms. So I can visualize them. Here's a gibbon. Here's another gibbon call. And this is not a gibbon call. So now I have a little data set. How would I actually build a CNN to take this little data set that I have and classify acoustic events of gibbon and not gibbon? So I just wanted to it's a bit fast, but I just wanted to show you. So this is essentially a very simple CNN model. So here you'll see that I'm creating a convolutional layer, which is in TensorFlow, it's written as conv2D, which means two-dimensional convolution. Here you'll see I'm saying I want 32 filters, and I want each of those filters to be a 3 by 3. So these are 3 by 3 filters. There's 32 of them. And I want to apply the ReLU activation function. And here I'm just saying my input is this size. Let's not worry about this because I haven't formally defined it. You'll see here, I'm now adding a max pooling layer. So in TensorFlow, we can add max pooling by saying max pool 2D. It's a two-dimensional max pooling. We spoke about this on Wednesday, and it's a 2x2 max pooling. Okay, so now we have more layers. So here's another convolution layer. Again, 32 filters. Each of those filters are 3x3, and I'm applying the ReLU activation function again. Now my next layer is another max pooling layer, a 2x2. Okay. Now, this is deep learning, right? So we need many layers, right? So here's the next convolution layer. In this case, I want 64 filters, and the size of each of those filters is a 3x3, and I use the ReLU activation function. Now, these are all hyperparameters. These are values that I decided. Remember, we spoke about flattening when we go from this object that has a width and a height and a depth, and then we create these very long vectors. We spoke about this on Wednesday. We can do it in one line of code, and it's called the flatten operation. And here, okay, so I've created this as a for loop, but let me take it out as a for loop. Here, you'll see how do we add fully connected layers. In TensorFlow, if you want to add a fully connected layer, it's called the dense layer, and you tell it how many units you want. How many of those circles do you want? And I want a ReLU activation function, and then I can add another one. And then, so I see your hand up. I'll take it now. And then finally, the last bit of the puzzle is the output layer. Because it's a binary classification problem, I want 2 units and the softmax activation function. So you can see that everything we've been speaking about this week, all of those complex ideas, all of those things can be written as one line in this library called TensorFlow that allows us to create these neural networks. Nomzaza, you have a hands up.
Yes, thank you. I actually only have 2 questions. The first one is, can we use a better activation function than ReLU? Because it's been observed that it tends to create like sparse vectors. And secondly, why did you decide to use Atom as an optimizer instead of the SGT?
Okay, so yeah, sure. There are new activation functions, and it's actually a fun project. I have a fun idea that if any of you want to work with me on how to evolve these activation functions automatically. But anyway, that's a separate topic. Researchers are, proposing new activation functions. It's very common for people just to use the ReLU activation function. It's been shown to work very well, but one could explore different type of activation functions if they thought there was a need to do so. My advice is always start simple, start with what works, ReLU works, and then if it doesn't work for you, try different things, try different activation functions. This is unfortunately the complexity with these deep neural networks, is there's a lot of hyperparameter tuning. That was your first question. Your second question is, why am I using the Atom optimizer? So over time, people have found more interesting optimization algorithms that are less prone to problems in the search space. Atom is one of them, where it can overcome some of the limitations that might be existing in older optimization techniques. Remember, optimization is essentially a branch of mathematics, right? So it's an active area of research. People try to find new optimization algorithms all the time. It just happens to be that Atom is a modern, good one that works quite well in general. So that's why in this script, I just used it. But that would be a huge discussion on its own as to what it is and the reasons for using it. I just wanted to show everyone that with a few lines of code and with the theoretical understanding that you now have, from a programming perspective, it's not too bad. It's a few lines of code and we can build these models. Since we have 3 minutes, the last thing I wanted to show you was if we executed and trained such a model, how does it perform? Here you can see a spectrogram that does not contain a given vocalization, and I'm predicting on it. Now remember, since we have 2 units, it outputs two values. And the one on the left is the non-given and the one on the right is given. So basically the model is saying there's a probability of 0.63 that this spectrogram does not contain a given vocalization, and it's essentially right. And a probability of 3 that it contains a given vocalization. Again, with this spectrogram, the network is saying there's a probability of 0.6 that it does not contain a given, and a probability of 0.3 that it contains a given. So it's getting it right. Here, this one clearly contains a given vocalization, and here the model is saying there's a probability of 0.99 that it contains a given, and a very small probability that it does not contain a given. So it got it right. And here is another one where it clearly contains a given vocalization, and the model is saying, I'm very confident that it contains a given vocalization. So that's it. I just wanted to share a little script with you and show you that in a few lines of code, of course, there's a lot that happens behind the scenes, but from a modeling perspective of these CNNs, we can write them in a few lines of code and do all these incredible things. So thank you, everyone. Yeah, so a 2D convolution is used for an image problem. And since we can represent audio as spectrograms, it's essentially an image problem.
Emmanuel, I see there is one question, one raised hand. Mpumelelo.
Okay.
Sorry, I forgot to.
Ah, okay. Okay, that was an old hand. Okay, Isaac now.
Hello, Emmanuel.
Hi.
Please, I would like to understand that. Okay, I would like to understand that from what we are doing now. Okay, first of all, if you have the audio, we'll try to convert the audio to an image, and then we'll go ahead to do the classification or whatever it is.
Yeah.
I don't know if my question is clear.
Yeah, so the steps you've described are right. We go from an audio, we create spectrograms, and then we create a convolutional neural network, because remember, a convolutional neural network, at least the one we've seen so far, is applied to image problems, and we can represent audio as image problems via spectrograms.
Okay, okay, thanks.
Great.
Okay, then Emmanuel, then if there are no more questions, it's then my pleasant duty to thank you very much for your time. And sorry, I was trying to sort out a little issue with Zoom because people that want to join for the ceremony can't manage to join us. But maybe Benjamin can share the secret link with everybody on Slack. Yeah. Sorry, Benjamin. Sorry, Emmanuel.
That's fine.
No, thank you very much, Emmanuel. I think you heard from the reactions of our participants that your lectures was very well. Your lectures were very well received, And I enjoyed them also very, very much. In particular, today was really the highlight of the series. It was really very interesting. I learned a lot of things that I didn't know. That was really nice. And I will play with it because I find it really fascinating. Thank you very much for that. Yeah.
Thank you, everyone.
And okay, I won't thank the participants because we have now a little closing ceremony.